Good morning. Today I am going to present about cache memory. It is one of the most important components in modern computer system, and we will understand its architecture, working principle and performance. Why cache memory is needed? In modern computers, the CPU is very fast and can execute millions of instructions per second, but the main memory or RAM is much slower. This creates a speed gaps where the CPU has to wait for data. To solve this problem, cache memory is used as a bridge between CPU and RAM. It reduces latency, improves speed and increases overall system performance. Next, memory hierarchical overview. In memory in computer system, it is organized in hierarchical. At the top we have very fast and small memory. At the bottom we have slower but larger memory. Cache memory sits in the middle, providing a balance between speed and size and helps in fast data access. Next, what is cache memory? Cache memory is a small and high-speed memory located near or inside the CPU. It stores frequently used data so that the CPU can access it quickly instead of going to slow RAM. It is built using SRAM and works automatically without programmer involvement. Characteristics of and types of cache. Cache memory has the three main levels. L1 cache is the smallest and fastest, located inside the CPU core. L2 cache is slightly larger and slower, acting as a bridge. L3 cache is the largest and shared among cores but slower compared to L1 and L2. Each level helps improve performance by storing important data. Next, how cache works and locality. When the CPU requests data, it first checks the cache. If the data is found, it is called cache hit. If not, it is a cache miss and the data is fetched from RAM. Cache works based on the principle of locality. Temporal locality means recently used data will be used again, and spatial locality means nearby data is likely to be used. Cache mapping techniques. When cache is brought from RAM to cache, the system must decide where to store it. This is done using mapping techniques like direct mapping, associative mapping and set associative mapping. Among these, set associative mapping is commonly used as its balance performance and cost. Next, cache performance matrices. To measure cache performance, we use matrices like hit ratio, which shows how often data is found in cache, and miss ratio, which shows how often it is not found. Another important measure is average memory access time, which helps in evaluating overall system performance. Next, example calculation. For example, if a cache access time is 2 nanoseconds and RAM takes 100 nanoseconds, which is 5% miss rate, the average memory access time becomes 7 nanoseconds. Without cache, every access would take 100 nanoseconds, which is much slower. Next, cache coherence and optimization. In multi-core system, each core has its own cache. Cache coherence ensures that all cores have consistent data. Protocols like MESI help maintain this consistent. Optimization techniques like fetching and writing cache-friendly code further improve performance. Next, conclusion. Cache memory has many advantages like reducing memory access time and improving performance. However, it is expensive and has limited size. Despite this, it is essential in modern systems like CPUs, GPUs and embedded system. Thank you.